Good afternoon, good evening, good morning. We are going to do a derivation here to find the potential difference between any 2 points near a point charge or a spherically symmetrical charge distribution. Whew, I should have been waiting all day for that. We are going to start off with the definition of potential difference based on your knowledge of the electric field, which goes a little something like this. For a tiny change in position, so if you take a little tiny step of length dl, the change in electric potential is equal to the negative of the electric field at that point dotted with the tiny little step you took, vector dl. There will be a separate video, I think, that will hopefully make more sense of where that comes from. But we're going to start with that. Okay, so again, the charge geometry is a point charge, so let's have one. By the way, what we're going to come up with is the very familiar result. This is going to be our end result. I'm going to write in the upper right-hand corner, V equals KQ over R, which the very perceptive of you will notice is not a change in potential. That is potential at a point. So that's going to be the end result of this. Of the potential at a point near a point charge. And again, that is not delta V, that is V, the potential at a point. But this expression that we're going to come up with does depend on the accepted value that at R equals infinity, that is where the potential is equal to 0. So that's kind of there's your difference in potential, because the potential at a point is a potential difference between that point and infinity. Whew, okay. So back to the original diagram. I'm now looking at this point charge, or the spherically symmetric charge. And for the sake of argument, we're making it positive. So this is positive Q. I'll throw a Q in here because it's fun. And this thing does create an electric field in the region of space around it. And of course, the electric field has radial symmetry. And there's an attempt to diagram the electric field. And the electric field can be expressed with the following equation, which we have already derived using Gauss's law. The electric field at a point near this point charge is equal to, of course, K times the amount of charge Q over R squared, where R is a distance measured radially from the center of the point charge. So this is like an R-axis. So if I'm at point P, I'm going to label a point P here, and I'm interested in the electric field at that point. Well, the distance R is measured from the center of the point charge to that point P. That is your distance R measured from the origin of your polar coordinate system, I guess, which is where R is equal to 0. So here is the origin where R is equal to 0. All right. Kind of making a point that we are using kind of a polar coordinate system, because the other thing that I want to do, the definition of electric potential difference, dV equals, I'm now looking up here at the top, dV equals negative E vector dot dl vector, depends on our having an expression for the electric field as a vector quantity. This expression for electric field that we've written only gives us the magnitude of the field. Now we know what direction it points. It points away from the point charge. So how do we turn this into a vector equation? And so how do we get the direction of the field at point P? In fact, I'm now going to add an electric field vector at point P. These blue lines that have been drawn are these pretty lines of force, but an actual electric field vector at this point is going to be, that's supposed to be along the same line as the radius, is R. So this is my E vector. It's a pretty lousy diagram, but we'll deal. So how do I turn that equation for the magnitude into an equation that shows the vector pointing in that particular direction? I'm going to make use of a unit vector. If this red arrow is the vector quantity that goes from the origin to point P, all I want to get out of that is this E vector, this green E vector that I have here, has a magnitude of KQ over magnitude of R squared. Nothing in this equation yet is a vector. K is a scalar, Q is a scalar. This R in the bottom here is the magnitude of the distance from the center of the charge to point P. So I'm going to get rid of my little arrow. So I want to introduce the direction that this electric field vector points. And again, I'm going to use unit vectors. I need to get a unit vector in the direction of this r vector, and I will use the fact that if I divide, consider this, if I divide a vector by its magnitude, what do I get? Well, I get, so just this is how I get a unit vector, but let's just consider an easier question for a second. So I'm going to go off on the right and just ask a similar question. If I have a vector, if this is a force vector, okay, and it's 8 newtons and it points east, okay, if I divide this force vector by its magnitude, then I'm going to divide 8 newtons east, that's the force vector, and if I divide that by its magnitude, the magnitude of the force vector, which is 8 newtons, I get 1 east, okay? That would be a vector, and I put this F with a little hat on it, and to be honest, I can't remember if we've done this before in class this year or not. This is how you get a unit vector in whatever direction you want, by dividing a vector in that direction by its own magnitude. The magnitude divides out. You get 8 newtons over 8 newtons, which is 1, and you get 1 east, which is a unit vector in the direction of that force vector. Okay, I'm going to get rid of this force vector. That was just for example. And now I'm going to go back to this problem. This red r vector is the position vector of point P with respect to the origin of our polar coordinate system. If I divide that by its magnitude, I get a unit vector in that direction. Remember, a unit vector doesn't have units, it just has a magnitude of 1, not 1 meter, just 1. And so if I now throw this unit vector at the end of my electric field equation, I now have what's temporarily inside the blue box. That's the magnitude of the electric field. The unit vector here is 1. It just gives me the direction that points in the direction of my red position vector for point P. And so I've now turned this magnitude into a vector in the correct direction. This now, without all these blue boxes, so I'm going to get rid of the blue box and the blue arrow, what remains is the electric field vector. Whee! That's fun. Okay, so now I want to find the potential difference between 2 points in the region near this point charge, near the spherical symmetric charge. So I'm going to start a new diagram just because this one's getting kind of messy. So I'm just going to do this I'm not going to draw that electric field again. This is plus Q. And here was point P, and which I'm now going to name point A because P doesn't suit me. I like A because I know another letter right next to A in the alphabet, which is B. So I'm going to go to point B, which is somewhere else. All right? And I'm now interested in finding the potential difference between A and B. By the way, it matters if I go from A to B or if I go from B to A, because in one case I'll be traveling to a point of higher potential, and another point I'll be traveling to a point of lower potential. I will tell you in advance that if I go from A to B, V, A to B, B is at a lower potential than A. I'm going to a point of lower potential. The potential difference, delta V from A to B, delta V A to B, is going to be a negative number. It's going to be less than 0. Whereas if I go from B to A, I'm actually going to a point of higher potential, and so delta V from B to A would be greater than 0. So it matters which direction I'm traveling. I'm going to go from A to B. Not that it matters, but I'm going to go from A to B for the sake of argument. Okay, how am I going to do this? The way I'm going to do this is I'm going to take a zillion little steps, and how I get from A to B doesn't matter. I can remember, I'm taking a walk, and I can walk in a straight line, or I can walk in a curvy line if I want to. Remember that the electric field is a conservative force. The electric force is a conservative force. And so the definition of a conservative force is that the work it does on a charge moving from A to B is independent of path. So the change in potential energy from A to B is independent of path, so the change in potential from A to B is independent of path. So it doesn't matter how I get there. All right. What I am going to do, though, is I'm going to write down what derivation I'm going to be doing here, which is to find the difference in potential from A to B. So I'm going to break this path into a bazillion little tiny steps, and I'll draw one of them. Okay, one of these steps has me going from here to here. I'm on this red path, and this is an infinitesimally small little step, even though it looks huge. And so this little tiny step that I take has a particular direction. It is dl, which, if I draw a really tiny arrow, I'm going to make this dl vector bigger just so we can see it. So the dl vector, I've scaled it up so you can see it. This is the dl vector, which represents traveling from one little tiny step to the next little tiny step, like that. And remember that the definition of potential difference traveled along that step is equal to negative the electric field at that point dot dl. All right. So, okay, what's the electric field at that point? Well, I now have an equation for it, and I can also draw. So that point, of course, is the beginning of this little tiny step or the end of the little tiny step. It doesn't matter because the step is so tiny. And the electric field at that point points away from the positive point charge. So it points in this direction. That's the electric field vector at that point. And then, of course, I have an angle between these, an angle phi between those two vectors. So I'm interested in the dot product of those two vectors because the negative of the dot product is equal to the change in potential I experience traveling from this little mini point A to this little mini point B, the beginning to the end of that little tiny step of dl. Okay, what is that dot product? I'm using a new color. Okay, well, it is negative E dot dl. For E, this E vector, I'm going to plug in the expression that I came up with earlier, which is K Q over R squared times the unit vector R hat, dot dl. Okay, this is the change in potential for what's teensy tiny little step. So what is this? What is this? I'm going to integrate, and I want to get this down to one variable. And so this is what I'm going to do. I'm going to say, what is this dot product of r dot dl? Well, r is a unit vector in the direction of the electric field. So I'm going to draw, I think, a nice new color. Whoops. What do I want? Just a pen. I want that. Okay. So my r vector, which is going to be purple, is the same direction as the E vector, but it's a different vector. So I'm drawing this r hat, r unit vector. And what I'm interested in then, as I say, is the dot product of r hat dot dl vector. All right. What is that? Well, the dot product of any two vectors, A vector dot B vector, is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And another way of looking at it is that it is equal to the magnitude of one vector, A, times B cosine phi, which is the component of B in the direction of A. Another way of looking at the exact same thing. So what do I get in this case? Well, if I look at the component of dl in the direction of the r hat vector, that is going to be, can I have any more vectors here? I'm going to use green. The component of dl in the direction of r hat is this guy, but it's purely coincidence that it looks like the same distance as r hat. R hat, remember, has a magnitude of 1. Not 1 meter, it has a magnitude of 1. But this green guy right here is, and you know what? This is where I wish I had a pause and I could go back and edit, because I'm actually going to take out this green guy. Ignore the last 30 seconds, because the component of dl in the direction of r, I'm going to draw it without an arrow on it. I always draw arrows, the components with arrows on them, but the component of a vector is a scalar quantity. So this is the component of dl in the direction of r hat. And what I want to point out here is that what that is I'm going to say it is dr. Okay, what is dr? Dr is what is the change in the r vector, the magnitude of change in the r vector when I went from the first point here to the second point. So in other words, this is the first r vector at the beginning of my little walk. Here to my magnified view of dl, here's the r vector. So here's my first r vector, here's my second r vector. Dr is the change in the magnitude of those vectors. It's a scalar quantity. And dr is also the component of the dl vector in the direction of the electric field. So it is, for the purposes of this dot product, this b cos phi. It is the component of dl. So the dot product is equal to the magnitude of r hat. So I'm actually looking at this thing right now, where this is r hat. Boy, am I doing a crappy job of this. And this vector b is my dl vector. And so the dot product is the component of a, which is r hat. Well, what's the component of a unit vector? It's 1. So this is equals 1 times b cos phi. And b cos phi is the component of dl in the direction of the electric field, and that is 1 times dr. This maybe seems really obvious, or maybe seems really subtle or something. I don't think it's completely trivial that what's inside the red box here ends up being dr. Okay, it's a scalar, and it is the change in the magnitude of how far you are away from the center of this charge from the beginning to the end of your little tiny walk. Okay, the rest of this does become fairly trivial, because dv is now equal to negative k q over r squared dr, which is a scalar quantity, that dr thing is. And so I now have all this expressed in terms of scalars, which is good because dv is a scalar. And now to get delta v, we're almost done, is I just say it's all those dv's added up. And so I'm going to integrate negative, I'm bringing the negative outside, k q over r squared dr. And I'm going to integrate from the beginning to the end of my path from point A to point B. So I'm integrating from A to B between those two positions. But those two positions measured, my integration variable here is r, and so what I'm actually integrating is how far those positions are away from the center of the charge. So I can write this as negative integral r, the distance that point A is from the center, it is small a, RB, negative k q over r squared dr. Now this becomes truly trivial. Delta V is equal to, let's see, negative kq. All that stuff is a constant, negative kq. And then I'm integrating, I'll write this down one more time, from RA to RB, dr over r squared. Okay, this is an easy one, negative kq. The integral of dr over r squared is negative 1 over r, negative 1 over r, and I have limits from RA to RB, and this is cake at this point. I have to be careful with the minus signs. I'm going to keep them all in for right now. Negative kq. I've got negative 1 over RB minus negative 1 over RA. Okay, so I got minuses all over the place. Pretty sure I haven't made any sign errors yet. I will distribute this minus here into my brackets. And so I end up now with delta V is equal to KQ times 1 over RB minus 1 over RA. Okay, what is delta V? Delta V is the change in potential at B minus that of A. So I'm going to actually write this as VB minus VA equals KQ, and again I'm going to go brackets 1 over RB minus 1 over RA. Okay, so why did I break up the delta V? Well, because as we saw up at the top here, what I'm going to end up with is actually an expression for V as a function of position, not delta V. And if I take either one of these points, it doesn't matter which one I choose, A or B. If I say let position A be infinity. So that's, by the way, that's not exactly the right statement. I want A to be infinite distance away from the charge. And then I define V at infinity to be 0. Okay. Then, if I go back to my original expression, I say VB, gee, I don't know what that is, but minus VA. VA is V at infinity, that's arrow 0, equals KQ times 1 over RB, that's whatever it is, minus 1 over RA. Well, I'm letting that distance be infinity. 1 over infinity, last I checked, is 0. And so I then have VB is equal to KQ over RB, and that makes me happy. I think it really does. Thank you.